All right, guys, so in this video, we are looking at a block that is sitting on a ramp. Initially, it says that a mass of 2 kilograms is placed on a frictionless inclined plane of angle 30 degrees. All right, so the first question wants us to find the acceleration down the ramp. Now, I know it's tempting to think of kinematics here, but think about the fact that we don't really have any information for kinematics. We don't have any distances, we don't have any speeds. Yeah, it starts at rest, but other than that, I don't really have anything at all. And so instead of going with kinematics, we're going to try to look at the forces because I do know something about the forces. I'm going to draw a free body diagram. I know that the force of gravity is downwards. I know that there's a normal force going up in this direction. Notice that I said a normal force. It's the normal force of the ramp pushing up there, okay? And it pushes up at an angle because it can only be perpendicular to the surface. Now, if we balance this out, right, we're going to draw our new axis where this is the x-axis and this right here is the y-axis. Okay, I'm going to look at the horizontal forces and I'm going to look at the vertical forces. Remember that this angle up here is 30 degrees because FG used to be on the y-axis and I've tilted the y-axis 30 degrees so that x is now parallel to the slope, which means that I've moved y over an angle of 30 degrees. Okay, so I'm going to break this into components. You guys hopefully are getting a little bit comfortable with this now, to where we can do that. I do know that the force of gravity is equal to mg, and it gives me the mass there, which is 2 kilograms. So Fg equals 2, and it is 2 sig figs, which is good because my g is in 2 sig figs as well. So times 9.8, and I get a value of 19.6. Okay? And so I know the force of gravity is 19.6. But that's not in the horizontal or vertical direction. I really want to be able to put it in the vertical direction and the horizontal direction. Why? Well, what direction is the block accelerating here? It's not accelerating vertically, according to my new axis. It's going to accelerate down the ramp. And so because the acceleration is in my horizontal direction, now this acceleration, remember this acceleration is not a force, okay? The only forces are gravity and the normal force, but I do want to recognize that the acceleration is horizontal down the ramp. And so what I want is I want the forces that are in that direction. So I want this guy right here. That is the only horizontal force that's showing up in my drawing because there's no friction right now. Okay, so I want to find that component. You'll notice that it is opposite the 30 degrees. So some of you are probably to the point now where you can go through this a little bit quicker, but I'm going to write that the sine of 30 degrees, sine because it is opposite, which is that FGX that I'm looking for, over the hypotenuse. So opposite over hypotenuse. Hypotenuse was that 19.6. That's the overall force of gravity here. And that should then allow me to solve for the force of gravity in the x direction, which is 9.8 newtons. And so I get force of gravity in the x direction is 9.8 newtons. And that is the only horizontal force. So now I can go into Newton's second law, and I can say the sum of the forces horizontally is equal to the mass times the acceleration horizontally. The sum of the forces, well, there's only one of them, it's 9.8. Now, you can determine what your positives and negatives are, okay? I'm going to say that down the ramp is positive. I'm going to define that as positive because that's what I expect to happen. I expect it to go down the ramp, so I'm going to find that as the positive x direction. The negative x direction is the direction that I don't expect it to go, which is up the ramp. So I'm going to go 9.8 equals the mass, which was 2, times the acceleration. And so we can divide by 2, and we get that the acceleration is 4.9 meters per second squared. We just calculated the acceleration using Newton's laws. Okay, now that was part A. Part B now says, now hang on a second, no friction is not very realistic. So what is the minimum coefficient of static friction that's required to stop the block from sliding? Okay, well, what direction would friction be going? Remember that it's accelerating down the ramp here in the positive x, what I define as the positive x direction. So what direction does friction need to work in order for the forces to be balanced so that it doesn't slide? Well, friction needs to be pointing up in that direction, up and to the right. Okay, and how much friction does there need to be? Well, the amount of friction must equal whatever the force is that was going down and to the left. So the only horizontal force before was that horizontal piece of gravity, which was, as we pointed out, 9.8 newtons. So in order for friction to balance that, friction must have a value of 9.8 newtons so that the forces balance out. Now, the question is asking for the coefficient of static friction, right? So what is the minimum coefficient of static friction? Well, remember, static coefficient of friction is less than or equal to the coefficient of static friction times the normal force. Okay, so we're looking for this right here. What is the lowest number that would allow me to have 9.8 newtons of frictional force? So I want this to be 9.8. I'm looking for that coefficient of friction. Now I'm looking for the lowest possible value here. So I'm going to find out what the value is when it's equal to 9.8. Any bigger number would give me a number bigger than 9.8. But I'm looking for what is the smallest number that this could be so that I get a result of 9.8 newtons for my friction. Now, you'll notice that in order to do that, I need to know what the normal force is. So I'm going to go back to my free body diagram, which is getting a little messy now. So I'm going to redraw it here just so that it's a little bit easier to see. So we had the normal force going up this way. That's important because that is the interaction between the block and the ramp. We've got the force of gravity here. And then we drew in our axis like this, where we have x and y. We identified the angle here was 30 degrees. We said that friction was going back in this direction. And then we got the components there. Remember, we talked about the components of the force of gravity. So given this situation, what does the normal force need to be? Well, we can look at the vertical forces, these guys right here. Okay, I'm no longer interested in the horizontal part of gravity or the horizontal friction. What I want is the normal force, and the normal force is completely vertical. And so I'm going to balance the vertical forces. Vertically, I can say that the sum of the, let me change back to here. The sum of the forces vertically is equal to the mass times the vertical acceleration. Now the vertical forces are the normal force, which is upwards, and the vertical force of gravity. So minus the vertical component of gravity. And that should equal the mass times the acceleration. But vertically, along this vertical axis, it's not accelerating. The only acceleration is down the ramp, which is our horizontal. So I can say that my vertical acceleration is 0. Now remember, I'm looking at my new vertical, my new y-axis. I'm not looking at the up and down. Obviously, the block is accelerating downwards as it goes down the ramp. Okay? Now at this point, we can find the gravitational force in the y direction. That's the adjacent side there, so that's going to be cosine. So we'll go the normal force minus, and similar to what we did over here with the horizontal, this is going to be 19.6 cosine of 30. And if we work that out, then we should get a value of 16.97. So the normal force is equal to 16.97 newtons, which, yes, in sig figs is only going to be 2, but for now we're going to keep all those digits. So now I know the normal force, and so I'm going to take the normal force and put it in over here, 16.97, and now I can divide the 9.8 by the 16.97, and we get an answer of the coefficient of static friction must be equal to 0.5. Now I got 0.5774, so 2 sig figs I'm going to write as 0.58. All right, now I want you to recognize that this is the smallest value that it could have, right? The static coefficient of friction could be larger than that, and that would have an ability to have a larger static force of friction, but it doesn't have to be providing that right now. Right now, all it needs to provide is the 9.8. All right, so there we go. We got the coefficient that is necessary to keep it from sliding down the ramp. We're moving on to the last part of the question here, which is, if there was no friction, could we find the speed of the block if it starts at the top of the ramp that has a height of 1 meter? Okay, so if the height is 1 meter, could I then determine the speed of the block at the end? Well, we're talking about speed now, so in order to figure out if I'd be able to do that, I'm going to go to kinematics, right? Because I'm no longer talking about forces and acceleration. I'm now talking about speed. So speed at the bottom of the ramp, that would be v. Okay, I just calculated the acceleration in step A, so that would be 4.9 meters per second squared. I know that the initial position is 0. The final position would be the length of the ramp there, because that would be the length. Don't use the 1 meter, because that's only the height. I need to use the distance, the displacement that the block is going through. And so I can use trig to do that, right? I have the opposite side, so I can relate the opposite to the hypotenuse. So I could go sine of 30 equals the opposite over the hypotenuse, which is that final length, the hypotenuse that I'm looking for. I'm going to multiply by x and then divide by sine of 30, and that hopefully will give us a value of 2. And so we know that x equals 2 meters there, so we know that our final position is 2. We know that if it starts at the top of the ramp, it doesn't say it starts at rest, but we can go ahead. If we know that it starts at rest, then yes, we should be able to answer this, right? We'd have enough information if we know the initial velocity that we could calculate the final velocity. If we do not know the initial velocity, then the answer is no. We wouldn't be able to answer that question. And so that's the answer really that you should give there for letter C. Is if we can assume that it's at rest, then yes, we have enough information to put into a kinematics problem. If we do not know what its initial velocity is, then obviously we cannot calculate that final velocity there. Okay, so there you go. That's example number 10, and hopefully we can move along and try another one out. Let's go.